All right. Good morning, everyone. Today we have a new postdoc here to talk to us about his research. It's Dr. Martin Stringer, and he did his PhD at Oxford and Durham with Andrew Benson and Richard Ellis, then moved to University of Durham, and afterwards to Observatoire de Paris with François Combe. And today he'll also tell us about galaxy formation and evolution, what he has been researching in the last years.
Just turn it on. Okay, got it. Yeah. But the speakers aren't on, because I don't think, I'm afraid my voice probably doesn't need the amplification. So yes, the story behind the invitation is in part a collaboration with Claudio, which you can see a picture of here. And the superimposition of this atomic cartoon is part of the theme of the talk, which is to, rather than tell you for an hour about all the details of Claudio's and others' simulations, what I'd like to try and do is in the theme of one of my earlier papers, which I'll just plug very quickly here in case people are interested in details, which is to look at different modeling techniques which exist now and try and pull out from the results of them formulae for emergent behavior in terms of the physics that everybody learns at university and fundamental physical constants wherever possible. So this was actually done at the Kavli Institute for Theoretical Physics, which I should also plug, and was a collaboration between a simulation group, start embracing the technology here, a simulation group, which is Alison Brooks and Fabio Governatu, which is a different code, the gasoline code for those who work in this field. And what we did was actually pull out from that all the physics that was going in and see if we could, without running the simulation, correctly predict what the results would be from the same initial conditions. And here is Andrew Benson, who is one of my supervisors who works on semi-analytic modeling. So just as an introduction, because I'll refer to these a lot during the talk, there are two computational techniques in play. One is to try and put the most fundamental physics into the computer and then press go and leave the computer to calculate what will happen. It's a very, very crude summary, but it summarizes the philosophy behind hydro simulations, n-body simulations, and all of this category of modeling. The other category is to try and understand as much of the physics as you can before you use the computer and resort to the computer only to crunch through the statistics of the merging of structures, for example. And that's semi-analytic modeling has been characterized. And in this paper and in other work, we've tried to show that the two are complementary, they're convergent methods. And indeed, they overlap. We'll talk about this more later, but as you get to the resolution limit of a simulation, it becomes a semi-analytic model because you cannot, if you are down to a single particle, the computer can no longer handle the physics, and you have to tell it what has happened inside that resolution element. So many of the papers which I'll just briefly review today do deal with that problem as well. But have these modeling techniques actually got us anywhere, fantastic though they are? And this is another thread of my research which I'd like to present. And to do so, we should recap and look at what has gone before. So notably this paper, which is one of my favorites from the era where galaxy formation theory started to make sense. And it was by these two guys who are both amazingly still active researchers, some nearly 40 years later. That's Martin Rees and Jerry Oestreicher. And it's quite frightening quite how close to where we are now, they got without any computational tools whatsoever. So this was before I was born, before most of the people in the room were born. And yeah, in 77, which was a very good year for many things. This is a dangerous analogy because it begs the question of whether we, like this fantasy movie franchise, have maybe not progressed very far, and indeed maybe have gone slightly backwards. And I hope this is not true, but one needs to be careful. So if you look at the second page of their article here, back in the 1970s, you could say fantastic things like this. Einstein's equations have no characteristic scales. So what are they talking about here? Well, this will be the first part of my talk, which has this very approximate outline. But you'll notice that the blackboard is here, so I will probably digress. So the first is building on this question on that second page of the paper from the 70s, which is cosmic structures. Now we know that they look like this. They're purple and yellow. So the Millennium simulation has given us this picture that we have to cling on to for what's going on out there. But all of this is, of course, invisible. This is, in fact, a matter-only simulation, dark matter-only simulation, a famous one from now many years ago. And Claudia is involved in developing higher resolution, larger volume versions of this, which hopefully we'll be using in work here. But this is a classic one which is publicly available. We'll come back to that in a minute. But in the 1970s, structures were a bit more straightforward. And you can actually characterize the mass and radius, or the density of a structure. So the density is going to go like the mass of the structure over the radius cubed. So if we just add some constants in here to make this dimensionally correct, you can actually write down that this is going to scale with the cosmology. So in fact, for certain cosmologies, this is very simple. So for a matter-only cosmology, which was the case when galaxy formation, the nominal case when galaxy formation theory was forwarded, you in fact could write down this for a collapsed region of the universe. Now this is for quite a special set of circumstances, so it requires spherical symmetry, and we now know that the cosmology is slightly different, so you can adjust this, trying to remember factors of 2, to write down this, where this is very close to what I wrote down before, but not exactly, about 200. And this parameter is just Hubble's expansion constant. So already we have a sense for the density of these structures in terms of just Einstein's, or Newton's gravitational constant, and the expansion of the universe measured by Hubble. So this is telling us that the radii of structures is proportional to their mass to the cube root. And this is where I have to think very hard to make sure whether this is a numerator or a denominator. And these structures are evolving with redshift very approximately with redshift like this. Or I can write it more accurately like this, so that it is correct. But bear in mind that redshift dependence. So as structures over densities in the universe collapse, they are mirroring the background density of the universe at that time. So if we try and draw a figure to visualize this, and you look at the radius of structures as a function of their mass, then what you find is that they will line up at any given time along loci which approximately follow this relationship. I say you will, well, you can't see them. and this becomes very much the point. But theoretically, this is what is happening. And at high redshift, early times in the universe, structures will populate around one of these lower ones, and then as time goes on, larger and larger regions of the universe collapse. The reason for this is that in order to collapse at all, you need to reach a critical density. This is probably all coming flooding back for those of you who don't deal with it every day. Those who do use this condition very frequently. What you're looking for is you're trying to find a region which exceeds the background density by enough to actually collapse against the expansion. And in fact, there is a limit to this. There is a maximum structure which in a given volume of universe can collapse at all. And this is moving upwards in time. So if you look at low redshift or late times, then this population has migrated. So as the universe collapses around these overdense regions, structures here will have turned into structures up here. So the evolution of individual regions, which is including mergers and other effects, moves up diagonally through these loci defined by this. So I have to lose these equations now and just draw one other picture to help illustrate this. So to further illustrate this growth of regions collapsing, I can introduce the mass function here, which everyone deals with every day. So you look at the number of structures as a function of mass, or log m. So these are both logarithmic plots. So what's happening here is that your low redshift population merges and further regions collapse around it, and there's growth here. So this is a projection of this mass function, and the upper line is a projection of the top mass function. So larger and larger regions are collapsing and populating this region. So the next question is, do all of these regions host galaxies? And that's something we can come back to in a second. Just sticking for the moment with the structures, so just the matter, saying nothing about stars, gas, none of that. Just looking at gravity and the cosmology. You can take the structures out of the Millennium simulation, which is that image we looked earlier, and make this plot. And that's what we're looking at here. So here, this dotted white line is the locus that I sketched. And then the shading is the population of structures. And there are many at low mass, and very few, and indeed zero, at high mass. Now, this absence of structures here is that in the volume that was simulated, think of it as a real universe, why not? In the volume, the observable volume, there just hasn't been a structure that big that was overdense. It's just too improbable. However, these are very probable. The universe is full of them, be it a virtual universe or a real one. And then you can continue and either observe closer or run the simulation for longer, depending on your perspective, and you can look at the new trend at a later time, and the new population, which is still shaded in blue. The old trend is highlighted here in green. And what you can also do, which is always in the simulation case, which is great, is actually look at where the structures 10 billion years ago are now. What are they doing? And we'll come back to that again later. Before I do that, I'd just like to comment that there's an interesting feature here, which is that the structures here do not line up along these loci. So this theoretical sketch needed a little bit more thought, which is that these structures here which collapse at early times do not necessarily go away. So some are still there, and they are still holding that fingerprint of the cosmology from early times. So there's this population here which have not merged with anything else and are still there, and they pull the average down. But this only happens at lower masses. It happens more so, in fact, at the lowest masses, and then becomes less of a problem, less of a discrepancy, and then at high masses here, you're back on the trend again. Because all the big things have only collapsed now because there just weren't any earlier on. So you have this slight difference between a model of simultaneous collapse and a model of gradual hierarchical collapse. Great question. I wish I had a figure. Yeah, you can make that figure, and we have done. So these guys, well, we can look. This comes up later. I actually have the statistics for this end later on, which we'll look at. For the background structures, yes. Because at the beginning of the universe, there was only one time where things could collapse, because it only just started. Later on, it has the whole time scale of the universe. But it does rather depend on how you define the scatter, I would think. But certainly, qualitatively, I completely agree. So what you can also do is just count things in the simulation, which will bring us on to our next point. So as I sketched, you have 0, 10 to the 15 solar mass structures at redshift 2, but you have some now at redshift 0. And it's worth noting that here, the creation and destruction rate is obviously rather similar. But that's too much to drive on the board, unfortunately. But at this end, there is a lot of evolution in the distribution of structures. So this is all very well. We have a max. It seems like just the probability of distribution of matter in the universe is giving a maximum here. So this is fine. So we don't have infinitely large. We're not surrounded by infinitely large galaxies. There is some limit here. But what about this end? And indeed, does this end match up with what we see? So are these structures necessarily hosting stars or a galaxy or many galaxies? So this connection, we haven't said anything about that yet. And unsurprisingly, the guys in the 70s thought about this too, and it's in the abstract. So they claim from their calculations that structures in the range of 10 to the 10 to 10 to the 12 solar masses will cool so efficiently that they always collapse at the freefall rate. So what's going on here? Well, behind this statement is the basic idea that as these structures as these structures collapse, they get a heat up to some temperature, which is going to be dictated by their mass, their density, by this radius, and Newton's constant. And the claim is that when this approaches atomic energies, ionization energies, it will radiate that energy effectively, and then gravity will be able to take over and they will collapse. So this is going to happen at this point. So we've still just got fundamental parameters in here. So this is the circular velocity of the system. And the claim here is that this is going to be Yes, and electrons. Yeah, yeah. I had this really weird chip on my shoulder about baryons. I used it myself for years, and then I suddenly thought, well, it's actually the electrons that are doing stuff. So I've got this. I'm now on a crusade on behalf of leptons. So, but yes, thank you. I'm sorry. Sometimes I do speak too fast and or miss things out. Force of habits. However, there's a factor of 2 in here somewhere. But I've got a squiggle here, so I'm just going to leave it. So the claim is, from just the most ridiculously simple argument, that when you have a system with circular velocities of this order, which is completely set by 3 fundamental parameters, well, you can have the speed of light, I suppose, but as a fraction of the speed of light, there's only 3 parameters in there. The fine structure constant, the electron and hydrogen mass. You're going to get galaxies. Now, how on earth do we check this? Well, this is now done all the time. What we're looking for is the relationship between the galactic mass, which we try and measure from knowledge of stars and stellar populations, so the stellar mass in the galaxy, and the mass of the structure, which you could actually get from the virial theorem by looking at the velocities of the objects inside them. Or you can consider the mass function which we had and just assume that the largest galaxies are in the largest objects and the next largest are in the next largest structures, and so on. So simply by counting visible galaxies and counting collapsed structures in our models or theories, whichever you prefer, then you can try and deduce the pairing. So this is a paper by Ben Moster and his collaborators, which is now very well known. And they simply take the stellar mass function here, technology switch, pens, pointer. So this is simply counting galaxies as a function of their stellar mass. Now, if you flip this round, then broadly speaking, what you've got here is increasing halo mass along this axis, because there are very few of these guys and very many of these guys. And as we said before, there are very many small objects collapsed, but very few at the most massive end. So you've now got stellar mass as a function of halo mass just by counting objects and measuring the stellar mass, which is a whole seminar in itself. But fortunately, we can skip that and move on to their conclusion, which is encapsulated by this plot. Now, this axis is now saying the fraction of the available normal matter which has turned into stars inside the structure, which we presume to be there. There is an assumption. And here is the mass of the structure. So, lo and behold, there is a peak at 10 to the 12 solar masses. And this is a logarithmic plot. As well as having a chip on my shoulder about missing out the electrons, I also have a chip on my shoulder about logarithms, although I've been using them, because they're very bad for intuition. So that looks, well, it's like, okay, well, there's a slight preference for 10 to the 12. No. If you take out the logarithms, it's very pronounced. So the universe really, really likes making stars in objects of 10 to the 12 solar masses. So this does seem to fit rather conspicuously in with what was predicted earlier on. That's the total mass of the structure, so it includes the dark matter. This is at redshift 0. Coming to that, I promise. So we can go back to the gurus from the 1970s and check. But actually, there's a bit of a discrepancy, really. This doesn't quite add up so far from what we've said. Now, you can try and understand this by looking at this plot here, which I sometimes sketch, but I think it's probably better to look at the printed version. This is the cooling rate for ionized plasmas as a function of temperature or circular velocity. So if you stick this on here, it's pretty much straight in the middle. So what's happening out, if this picture is correct, then out here we're starting to lose material because it just simply cannot radiate energy. So on this linear plot, the radiation rate is 0 out here, but there is just enough to cool early. And as Claudia says, this is redshift 0, so we'll have to start revising this as we move through the rest of the seminar to consider hierarchical build-up. But here, we do have a bit of an issue with this simple theory, from what I've said so far, which is that this is the absolute peak of formation, but yet we've converted only a tiny fraction of the material to stars. So there has to be a simple explanation for this. You can make some excuses for the authors because the cosmology will affect the slight relationship between the position of the atomic cooling on this axis and the mass. So that does actually help them a bit if you update their ideas. But there's still a discrepancy which is encapsulated by this picture. Now, this wasn't really a problem for them, because all the other thing you could write in the 70s is this sort of paragraph. In order to keep our discussion short, it is of order of magnitude illustrative character. So they only have to get anything right to a factor of 10. Well, that in some cases is still true of galaxy formation theory, but we would like to try and do a bit better. So we should try and address this question of if all this material which has collapsed into these structures is not in stars, where is it? Now, I guess the answer for this is now well known, but the origin of the answer I didn't know, certainly not when I was a student. So to try and track down the first mention of outflows in galaxies, which is now a buzzword in its own right, I got back to this paper. There's a guy called Richard Larson who, again, is still researching. And I should also mention that his paper builds on this one by Matthews and Baker, so that is actually the earliest citation. But Richard Larson here crunches through the numbers and actually checks it. So this is a quantification of an idea from 71. So the idea here is that if you have supernovae going off in galaxies, then there is enough energy, and it is particularly effective for small galaxies. So the idea here is that you have the same explosions. The star doesn't care what galaxies it's in, and neither does the supernova. So the same process is happening. But in some galaxies, you have high potential wells, and in others, you have low potential wells. So this figure that we plotted of the conversion to stars, if we're looking at this region here, what's happening is at this end, gravity is sufficient to hold the gas in and form more stars. At this end, all of this material here is being expelled. But we should, subject to a time check, we should check this, and we do have time to do so. So the key here is that these low mass systems, I should give myself some axes here. So this is just the log of the mass, and this is the fraction that has been converted to stars. Lower escape velocity will mean that you can expel more material. Now, the most remarkable thing in this paper is that apparently in the 1970s we knew how much energy was coming out of supernovae. Great. How? Well, here's the number, 10 to the 50 ergs, which is a theoretically motivated fraction of the total. So this is the available energy. But there's no citation here. This would never get through refereeing now. So it begs the question, where does this number come from that was just common knowledge? So this ended up with me spending a couple of days in a very dusty library. And I got back eventually to 1967, and this review, not even a paper, just a review talk by Minkowski, the other one. And then I kept reading, And then from 1967, I found myself in 1572, suddenly. And I found myself looking at this object. Now, people who work on this field will now, probably can now go to sleep for a few minutes. But for those who don't, this is a remarkable piece of science that was done, which I can't resist saying. So, based on this picture, in the 1960s, we went back to look for the remnant of this supernova that was observed by this guy. So the moustaches in the 1960s were definitely not as good, but observing equipment was. So they picked up radio emission, and then here on this figure are plotted possible loci of the expanding remnant that are consistent with their measurements. So there is the location of, based on the drawing of Tycho's supernovae. Now, of course, it looks like this. And what is remarkable is that this front here, as the gas expands, has a momentum which is set by exactly this same feature. So at the same time, the simplest physics of atomic structure is constraining the way that the gas cools to the center of the structures, and at the same time, it sets a limit on the momentum of the shell as it expands, which, as we'll see, will control the amount of gas which gets back out again. So here's Minkowski's paper. So in order to get an energy from this, you just do speed equals distance over time, and then half mv squared. So here's the time, here's the distance, and then for the mass, for your half mv squared, you need to have a look at the column densities and pull out a mass that you assume to be contained within that volume. And it's a combination of measurement and assumption. So they reckon 3 solar masses of material is moving at what I would imagine is several hundred kilometers a second, and they pull out an energy of, it's difficult to see, but it's 10 to the 50, so 10% of 10 to the 51 ergs. And this figure is then used by Larsen in his calculations. And there's this key line here. So he equates this to the energy required to escape from the structure. Well, from the galaxy. They didn't have the cold dark matter picture there, which we now are running with. And we want to check it. So this is not a crusade to say that this dark matter picture is right. It is to push it and say, well, okay, if this is the right answer, does it actually work? And does it work without relying on computers to confirm every answer? So can we, and you can actually pull this out just from his paper and from our modern perspective. So what he's saying is that the outflowing mass times the escape velocity of the system had better be coming from the total energy available from supernovae. But we know what this is, because this is going to be the energy from each individual supernova times the stellar mass of the whole system divided by the mass that we require of stars to make one supernovae. So this is dependent on the IMF. So you're summing all the stars that are likely to form that will produce supernovae and dividing by the total mass. This turns out, so it turns out that you need about 80 to 100 solar masses of material to make one supernova. And the result of this is that it comes out, you can express this as a specific energy yield per mass of stars formed. So this is all consistent with what happened in this paper. And this number is of order 300 kilometers a second. And now you have an expression for the outflow mass as a function of the stellar mass. Now what was missing in the 70s paper is that we now know, or we are working on the assumption that all the mass here had better have come from the total normal matter budget in your structure. So now we're pulling out numbers from WMAP, the total baryon density. It's okay to leave the electrons out here because they don't weigh very much, and the total matter density. But we can, and now we've actually solved the problem. So the stellar mass inside a structure of total mass MV for real is going to be given by this, and then this crucial factor over here, which is the specific energy from supernovae and the escape velocity of the galaxy, which is the circular velocity or the velocity dispersion in the case of an ellipse field, depending on how you're measuring it. So the question is, did they get it right? Yeah, so you can motivate this by saying that all the gas goes in, forms stars, goes in once and out once. That's one way of looking at it. You can also derive something which looks almost exactly the same by a slightly better assumption of steady state. So the question, rather being how much of the cooled mass has been expelled, the question is rather what gas population can be maintained under the constant processes of star formation and supernovae. All it is a differential version of this, which brings out the same final line, subject to some geometrical factors. So what we all wanted to do in this is push this. So we wanted to push whether they had this idea correct, and we also wanted to see whether the simulations are backing this up. So this led to this paper, which is again a collaboration of sorts between simulators, cosmologists, here's Carlos Frank, Sean Cole, and observers, Richard Bauer, in part-time at least, and myself, who's pulling all this together and trying to test these ideas. So there's a figure here, which I'll just explain. This is now the figure that we've got used to, looking at the characteristic velocity, or from the virial theorem, the mass scale of your structure and the stellar mass that's inside it. Now, this is more direct way of measuring it is consistent with the Moster analysis, which I talked about, which is just looking at abundances. So the two are mutually consistent to the level of scatter in either approach. Now, in the paper, what we do is just straight away on the first page look at this traditional idea with in the light of modern data. Now, this blue line is what I wrote on the board. So it seems to broadly go through all the data here. Now, because in the clusters a lot of the material is still in gas, all of this data includes the gas content as best we can measure it. But this was pulled from work by Stacey McGough, so it's an entire paper in itself. What we want to do is run with the observations in the literature and see if they stand up to traditional and modern theories. Now, this blue line is tantalizingly close to correctly going through all our data 40 years later. But worth pointing out is there's another line here which is a different assumption, which I'd like to just talk about in some detail to summarize where we went from here in the paper. This line is exactly the same process of reasoning here, but it proposes instead that it is the momentum of the supernovae which is consistent. So inbuilt, I'm now pointing at this with my pointer, this is ridiculous. So there are some ideas here which I brushed over. What this is claiming is that you have an equality here. I'm doing it again. You have an equality here between the energy available and the mass that escapes. But for this to be an equality rather than a limit, you're implying that somehow the explosion knows how much gas to sweep out so that it precisely conserves energy. There's nothing in physics to say that you can't expel a small amount of matter very fast, for example. So, in our view, and perhaps in Richard Larson's view, this is very much a limit and not an equality. And yet, when we're producing the models that I talked to right at the start, we're assuming an equality here. So we wanted to just try and check this out. So in this traditional treatment, we're assuming that all of the supernova energy is dedicated to some portion of gas, and that gas then escapes. Whether or not this gives the right answer, I'm certainly not happy with this picture, and few people would be. A picture that we, on the paper at least, were more happy with is the idea of momentum conservation. So as this remnant moves out, it will inevitably influence a large volume of gas. And the energy that it gives to that has to be constrained by momentum conservation. So you'll get a spectrum. You'll get some material which is in a location such that it is hit by two supernovae explosions and gains a larger amount of kinetic energy. You'll have some where perhaps, in fact, the effect of multiple explosions cancels out. So over the entire galaxy, over its entire lifetime, you would expect a distribution of energies as a result of these explosions. Now, in the traditional picture, you have this imaginary process where it sweeps up gas on the way out and just satisfies this equality. Now, that holds up in our picture to the extent that only the most highly accelerated gas is going to get out. So the mass is in this tail. Now, the biggest problem with the original picture is that in the case of dwarf galaxies, it predicts a factor of 1,000 more gas removed than was there in the first place. In our picture, our picture is simply that more of the same distribution is removed because of a lower potential barrier. The result of this, which was upheld by Claudio's simulations, that is at least a lunchtime seminar in its own right, but motivated by the combination of analytic theory and the results of the simulations, we motivated this form, which goes straight through the intermediate mass galaxies here. Better than either of the lines we had before. The idea being that at low masses, momentum constraints are important. At high masses, energy limit, as predicted in the 70s, is still valid. But for the dwarf galaxies, we felt that the limit was more to do with the cooling limit and stripping, which was covered in a separate paper, which I'll have to skip over here, but if anyone is interested in this particular field, I'd be delighted to chat later. So in the last 10 minutes, 5 to 10 minutes, I'll just address this last question, which is the evolution of these systems. So in order to try and make the cosmology which I sketched on the board at the start, in order to try and connect that with what we see, it's quite important to just retain the perspective where the galaxies are fitting themselves to the environment. Although in the simulations we can take an individual region and watch what happens with it over time, in reality we can't do that. This problem is shared by biologists. So, like them, we can look at fossils, so we can look at the old stars in a population and deduce what that would have looked like at earlier times. What we can do, which they can't, is actually look back in time. So if they looked back, they might see our origin as being this. They have worked it out from the other technique. But it is a bit of a stretch, if you didn't have that information, to think that this can turn into this. And it's particularly difficult when, in fact, the right answer was that it went via something that looked like this. So the moral of this story, certainly for me, is that nature does what the heck it likes, but it is subject to its environment and the conditions that it's in. And we wanted to take this idea to look at the very current problem of galaxy sizes. So this is another collaboration between observers. So here's Mark Curtis' company, who allowed us to use Cosmos data, and Francoise and Ben Moster, who I've mentioned already, and then theorists here who are trying to measure that against cosmology theory as best we can. Now, to do that, you need to have this idea of mapping between host structure from the cosmology and the galaxy, which you can actually see. So that's this figure here, which I would recommend to have a look at, which tries to summarize everything I've said so far in the seminar, which is on the archive. So these are the page proofs that's just been accepted. So going back to this figure very quickly to try and answer Ignacio's question, in the Millennium simulation, we can actually take these guys and say, well, what happened to them? So there's the top 10 structures in a bit of universe at redshift 2. Are they still the top 10 now? Well, the first guy is. Unfortunately, the others are nowhere near. They've been overtaken by totally different patches of universe, which just end up being bigger in the end. So this idea of connecting the order of things in the past and the order of things today is certainly not guaranteed or assured by the simulation techniques. In fact, so number 5, by the way, merges with 1. So they both turn into the same objects. So that's one thing to be careful of. And then the other thing is, even just in this small sample of 10, one of them goes backwards. It actually gets less massive. It becomes a satellite of a much larger system and has the mass stripped. So that's just a quick aside about the assumption of preservation of rank order with redshift, which is not upheld by numerical modeling. So coming back to this paper that we've looked at, now we can answer Claudio's question, which is the evolution of this relationship with time. Well, it's quite static, actually. This is a logarithmic scale, so this is significant change here. But the key with galaxy sizes is the equation that I had up here. It's the first thing I wrote down, which on a bigger board would still be there, but I'll just write it back up again. It's this idea. So this guy is evolving with time. Oh, I've gone backwards, sorry. So whilst on the left here we have the stellar mass as a function of host mass scale. Here we have the radius on this axis. So whilst the masses are remaining very similarly correlated, for the same stellar mass here, you get you are in a system of much, much greater physical extent. So the relationship between mass and radius here is evolving significantly over time, whilst the corresponding masses are not. And this is what we wanted to test against the data. So the best way to do this is to flip this figure around, including the axes, and then what you have is something which we can observe. You have a prediction here from very, very few arguments that I've presented here for the relationship between stellar mass and host radius. And from the host radius, because of the conservation of angular momentum as the system collapsed, we can test whether the galactic radiuses match that, whether they correlate directly, which would be the result of conservation of angular momentum. Now, this end requires a little bit of thought, which I think is really important. Although I'm pushing time, this is a very, very important part of our work to make clear. So there are two different questions you can ask here. A theorist will ask, what is the average stellar mass, what is the mean mode, median stellar mass for my dark matter or host structure at a certain mass? And the answer will be, well, roughly the same. So apparently not much change from redshift 2 to redshift 0. Now, if you're observing, of course, you ask a similar question. What's the average, what is the average host mass or characteristic velocity for my given stellar mass sample? And there you get a totally different answer. You'll see the evolution. And the reason is that if you're in a 10 to the 13, if you're a 10 to Milky Way mass galaxy here at redshift 2, you're probably in a 10 to the 13 solar mass structure, because there just aren't any up here. You can't be in one, so the average is bound to be much, much lower, close to the limit here at 10 to the 13. Whereas at redshift 0, there are plenty of 10 to the 14 and 10 to the 15 solar mass galaxies, and they're much more likely structures, they're much more likely to host a Milky Way mass galaxy, so you're probably in one of these. And this difference is crucial when comparing observation and theory. So just quickly illustrating that with mass function, you have the stellar mass function is not evolving very much because all of the galaxies are held by this atomic cooling limit, which I sketched very quickly on the board. But the structures are not held by that. They're evolving a lot, as we mentioned several times. And this is exacerbated even further when you look at radii, which is why this is such a useful tool for measuring our cosmology theory. So here we have stellar masses which are hardly evolving at all, but our host radii are increasing by a factor of 5. And if we go back to this more observable figure of radius as a function of stellar mass, and we look at the prediction from basic cosmology for 2 redshifts, we find significant evolution and, crucially, much higher evolution at high mass. This is because both samples, unfortunately all of this is difficult to observe, but we have got a handle on these two. If you look at categories of galaxy, samples of galaxies at high mass, you'd expect them to evolve much more than intermediate mass galaxies, because they are not only increasing with the cosmic expansion from this equation, but they are also hosted by larger masses. So both the mass and the radius are changing with time for these guys. So the last 3 figures then, this is just a look at the Millennium simulation populated with galaxies and how the 10 to the 11 solar mass category evolves, and then how the 10 to the 11.5 solar mass category evolves. The reason for this this intermediate category here is because we really can't observe any bigger than that. There just aren't enough galaxies in the universe to test that. So we have to look at these quite fine categories. This is just a quick figure to show that the mass of the host of a galaxy in this category is going up. So it separates out the 2 effects I referred to. And then finally, we can have a look at these against Mark's data. Mark and collaborators, of course. So here's Cosmos data for galaxy sizes as a function of time. And here is the basic prediction that I have on the board next to me, translated to galaxies. And here it bisects the elliptical and spiral categories. The idea being that although the formation mechanisms of these 2 types of galaxies might be quite different, ultimately it is the same quantities that are being conserved. The specific angular momentum from the host structure is still getting to the central system, but by a series of minor mergers rather than by dissipationist collapse. In both cases, they must conserve angular momentum, and we think that a signature of that is the lack of different evolution here. Now here we're looking at galaxies over 10 to the 11.5 solar masses, and we're struggling to make significant conclusions here, but certainly at the moment we're not disagreeing with the data here. So thank you very much for patiently staying with me as I go through 2 or 3 papers, and I'm here for 2 years if you have any questions. Thank you very much.
Yeah, thank you a lot for the nice talk. We have now a couple of minutes for a few questions.
Sorry.
So if you want to ask right now something.
Could you show us? Okay. Could you show us one of these view graphs where you show the deviation between, the ratio between the baryonic matter and the
yeah, sure. Might be quicker to just exit.
My question had to do with the fact that it is never the...
So, like this one, for example?
No.
No?
The one that you have also the ratio between the baryonic, the omega baryon, and the omega matter.
Yeah, sure. So
my question is, why is never... why it doesn't go to the ratio, to the omega baryon over omega matter?
Up here?
Yeah. Why is never that?
Yeah, this is true. I should... this figure, first of all, I should say that I brushed under the carpet a little the difference between measuring stellar mass here and baryonic mass. So look at the difference here. So this is now the best observational assessment of the total matter in clusters, and before was just the stellar mass inside. So which was your question appertaining to?
Actually, I can reformulate it here.
Sure.
Why these galaxies never reach this?
So these are estimates for total cluster mass.
But that's for clusters, right?
That is an outstanding. So up here, that is an outstanding observational conflict with theory. You can make if you look at the pie chart of the content of matter of these, then it is basically if you make the most generous concession to our observational ignorance, you can just about satisfy yourself that the theory is correct. But if you take our best guess, it is in conflict. So all the estimates from intra-cluster gas stellar masses do not add up to what we think should be there. So there is tension there, if that's your question.
No, actually, it was with these galaxies. Why?
These guys?
Yes, those that are not so massive, the disks.
Yeah. So
they never get to the...
Yeah, well, I think that's... well, there's... Yeah, the first order, on my conjecture and most of the literature, the first order is supernovae. So the energy from supernovae should excite, if you like. It's not a great word, but it should... it has enough energy to expel gas from these systems to account for this gap. So this blue line is a very simple application of this idea, and the red line is a similar idea, but assuming momentum conservation. And in fact, in my view, the momentum conservation one is closer to correct, but we preferred the slightly more developed model that I presented in the following few slides, which I won't go through.
Okay, thank you.
Martin, during years, the AGN feedback was something that people was considering for explaining the failure
these
of
guys.
the... Yeah. But, I mean, you have not mentioned at all AGN feedback. Is that because you don't think it's relevant, or is because it's the same mechanism or the same physics? What do you mean with that?
So the reason not to mention it is mainly to avoid this question. But no, there is no question that it is a correction which comes in after everything I have presented. So it is everything I've said about the zeroth order, which would be the atomic cooling limit, and the first order, which would be the supernova effect. It would appear from, in my view, the AGN is a third order correction to those. When you start getting from within a factor of 2 of observationals to within to less than that, to actually matching them.
Yeah,
so I agree.
I think that
that's the remaining part of the puzzle.
I will agree with that version. I mean, in the sense that recently the AGN feedback is being not so relevant. I mean, from the observational point of view, people is realizing that maybe it's not such relevant. No? So, and it's nice to see that here, from a theoretical perspective, is also...
Yeah, I think it's definitely the area to study, but in the meantime, we shouldn't forget about all the other factors which are in fact more dominant. Yeah. Glad you did.
This one, when you're talking now about the supernovae, what it means also is that more larger structures are more metallic, in the sense that if you lost the material from the supernova, you have not the enrichment.
Yeah, so the question is whether there's a net gain or net loss of metals as a result of supernova outflow, supernova-driven outflow. Good question. But carry on.
No, it was.
Yeah. So that you could in fact crunch through the same analysis that I did regarding just the mass, but then look at the mass of metals, and you'd find you need to make assumptions about how much of the material you sweep up is supernova-enriched material and how much is unenriched material. And the models that I talked about at the very beginning will make assumptions about that. And anyone who's an expert in that field should look at the models, see if they agree, and if they don't, write a paper about it. Because I suspect that many of the modelers would like to have that parameter, have that assumption more tightly constrained.
And also it affects the cooling and all this.
And it, absolutely, yeah. So the metal enrichment of the gas that's cooling is absolutely crucial, yeah.
All right. Is there no more questions? He said we have time for years,
but not at the end of the 2 years. Maybe in the first half, and then we can write about it.
Yeah. So let's thank Martin again for the nice talk and.